Hello, my name is Steven de Oliveira. This talk is about the Love smart contract language developed at OCaml Pro. I will start this short talk by an introduction of blockchains. A blockchain is a tool for independent and untrusted users who will work on the same network. Their goal is to agree on how to order a flow of messages, and this must be done as quickly as possible. Even though they are not trustworthy, they must not rely on a third party or centralized authority to agree on the message's order, because all users, especially third parties, are considered not trustworthy. In order to do so, every user has a copy of the chain. They all work on their own data and share it under a given consensus protocol. Emitting and validating a message on the chain modifies the global state of the chain. In the case of cryptocurrencies, messages are usually called transactions or operations, and executing a transaction modifies the balance of the sender and receiver. As everyone has a copy of the data and must agree on the validity of the transactions, cheating can be prevented. For example, it prevents double spending, which is the process of spending twice the same token. So modifying the state of the chain is a thing, but a more interesting approach of blockchain is not only to provide modifications per se of the chain state, but to provide a pseudo-user allowed to modify the state just like a real user would, but whose behavior would be encoded in logical and public rules. This is what a smart contract is. A smart contract is basically an algorithm deployed on the chain by any user, and it will act just like any other user on the chain. It has a balance, it has a memory, and it has logical rules on how to handle transactions it was sent, on how to modify its own memory, and how to emit transactions. Everyone on the network has a copy of the smart contract code in its memory, which means that everyone can replicate the execution and update its personal data accordingly. While the consensus protocol allows users to agree on how the chain modification must occur, smart contracts are defined by users, and as we said, users are not trustworthy. That's why smart contracts must be auditable. There are two kinds of smart contract languages. First, there are low-level languages that are executed on the chain, like Michelson for Tezos or the EVM for Ethereum. As contracts in such a language are executed on the chain, any proof on their code will be a proof of what actually happens on the chain. The issue is that the level of expertise required for even reading such contracts is much higher than the expertise required for writing them in a higher level language, which is the second kind of language used in blockchains. While they are easier to read, specify, and verify in general, they must be compiled to a lower level language that the chain will be able to execute. So our objective was to get rid of this constraint by providing on the chain the interpreter of a high-level language. So with Love, we wanted a high-level WYSIWY language. What you see is what you execute. We wrote it in OCaml for several reasons. Tools for developing a language, from a parser to an interpreter and all the logic in between, is mature and secure in OCaml. Also, as we targeted WYSIWY, we preferred to use the language already used for the blockchain protocol, which was OCaml. In Tezos and Dune, the chains initially targeted by Love, smart contracts are written in Michelson. We wanted our language to be at least as expressive as Michelson, but we also wanted to have decentralized libraries. Libraries are contracts with no storage, but only pure function. That's why we needed polymorphism. And in the meantime, we wanted to avoid a type inference. The idea is that inferring type is harder than just checking if they are correctly provided. Also, we did not want it two semantically equivalent programs, only differing in their type annotation, to be checked differently. Having a strongly typed language with no type inference led us to use the systemf type system, just like the Scila language. Love defines several built-in types. Integer and naturals are embodied arithmetical values, preventing overflows. As there is no operator for subtracting two naturals and that would return a natural, it also prevents underflows. Operations are the messages. They can only be generated by the primitives of the language and they work as black boxes. Addresses have their own type, different from integers, so there is no arithmetic on on addresses. Love provides multiple collection types similar to OCaml, plus a big map system that is proper to Tezos and Dune. It has tuples, functions, and the main component of systemf, the for-all type for polymorphism. In this demo, I will present what a Love smart contract looks like by implementing a voting algorithm. So, Love contracts are built from two components, type declarations and values. So, for a voting system, we'll need a type vote, which will be either a blank vote or a vote for someone. Then we will need a type for the memory of the contract, what will be stored. So let's say type storage equals votes of type address map vote, vote, and an end of vote, which will be a timestamp. So the type storage is actually a reserved keyword that represents what specifically the contract will save in its memory. There will be no actual value of the storage in the contract. All we know is its type. So we need three things now. We need a way to initialize our contract, a way to read it, and a way to write it. So first, let's see initializers. So there can be at most one initializer in a contract, because you can either initialize it with the actual value or through this function. So this function is called storage and takes one argument of any type. So let's say the duration of the contract. So we need an empty map for the votes, map.empty. So map.empty is actually a function that expects two arguments, which will be the type of the key and the type of the binding. Here is the type of map.empty. For all key, for all binding, key binding map. So in order to fulfill these two constraints, we need to set that the key is an address, the binding will be a vote, and now we have an empty map of address to votes. So now we have the end of vote, which will be current.time plus duration. So this is an operator for adding timestamp and natural, because as we said in Love there is no type inference, so we have one operator for each arithmetical values. And now we can return the storage end of vote. So the initializers return a value of type storage, which will be used as the first storage of the contract. Alright, so now let's see how to access the storage. So to do so, we'll define a view. So a view, let's say getVote, takes at least one argument of type storage and any number of argument of any type. So let's say here a voter of type address, and we want to return the actual vote of the voter. So he may not have voted already, so let's say that it's a vote option return type. So when you call getVote, you won't actually need to provide the first argument. It will be replaced during the execution by the current storage of the contract. So if we consider that storage is the current storage, we'll just need to access the map in the variable. So as for empty, find expects two arguments, address and vote, plus the voter and the map. So here the view takes an address and returns a vote option. The storage is just replaced by the current storage. Now let's see how to update the storage. And to do so, we'll introduce entry points. So entry points with initializers are the only functions and values of the contracts that must be accessed with a transaction. So you will send a transaction, for example, for voting, and this will trigger the execution. So just like for views, it will have a storage argument that will be replaced by the current storage. There is a second argument representing the number of tokens sent in the transaction invoking the entry point. And we'll have an argument of any type. So here, let's say a vote. And now let's vote. So we need a new storage in which the new vote is added. But first, we have to check that the vote hasn't ended yet. Otherwise, we want the execution to fail. So if current time superior to storage end of vote, then so this operator is polymorphic, so we have to specify its type. Then fail with is also polymorphic. We don't know the type of its arguments, so let's say we want to fail with a string. Voting already ended. And the return type of fail with also is polymorphic. So we'll say that it's unit. In, and now we can set the new storage. So let voter equals to current sender. In, let new storage equals storage with votes. Add. As for empty and find, we need to specify the types. Voter, vote, and storage.votes. So if you're familiar with OCaml, this syntax won't be much of a problem. And now an entry point actually returns two values to return a list of operations that will be put on a heap to be executed after the current execution. So here we don't want to generate any operation, so an empty list. And the new value of the storage. So this second element of the tuple will simply replace the current storage if the execution is successful. Then, as I said, all the operations in the list are put on a heap to be executed after. If any of them fails, then all the executions fail. So this empty list is polymorphic, so we have to specify its type. This is an operation list. And now we have an entry point that expects a vote. And that's it. To briefly conclude this talk, we compared the love contract implementation size on the chain with their Michelson equivalent. The bigger a contract is on the chain, the dearer it is to deploy in terms of CPU, but also in tokens because the actual cost of deploying a contract is proportional to its size. That's why optimizing their size on the chain was one of our priorities. Love contracts are about 60% smaller, hence 60% cheaper to deploy than Michelson contracts. One main drawback is that they are in general dearer to execute. This is mainly due to the storage serialization that is expensive when the storage is a record, because records hold strings for identifying the different fields. This cost is reduced by replacing records by tuples. In the future, we want to continue our optimization on gas consumption, especially when deserializing storages. Identifying efficient coding practices that would optimize love contracts is one of our targets, as well as introducing tail calling in recursive function. We would also like to extend the language with cryptographic primitives for zero-knowledge proofs, and also extensible records and pattern matching exhaustiveness. Thank you for your attention.